on this computer. Okay, so I want you to do this. We're going to start off by doing derivatives. Let me get the polls going here. Where are they? There you are. Okay, so we're going to start off by doing this question. Now, I know that some of you have seen derivatives before, and you probably know how to do the quotient rule for those of you, or the power rule, or the product rule. The answer is no. I would very much prefer that you do this using the limit definition of the derivative. When I take this question up, I'm going to use the limit definition. So for those of you who do know the more advanced tools to compute this, I still think it's worthwhile doing it by hand. And some of you might say, okay, well, this is a silly question because I can just plug this into Wolfram Alpha, right? Wolfram Alpha will give us the answer. Last year, I managed to give them a question on this that Wolfram Alpha didn't really help on. So doing this a couple of times, I'm not saying practice 80 of these questions. I don't think that's valuable. But you should practice doing a couple of these questions because I can totally make a question where Wolfram Alpha won't be able to help you. Neither will your derivative rules, for those of you who know the quotient rule and all those things. Okay, so give it a shot. Make sure you know how to do this by hand. But for those of you who know do know the quotient rule, you can check your answer that way, right? So give it a shot, and you can double check it. Okay, I'm going to give you about 40 more seconds just to see what you've got. So try and get your answers in. Okay, so this is pretty good. 60% of the class said B, and then, relatively fewer for A, C, and D. B absolutely is the correct answer. Now, there's a reason why I chose this one in particular. So I'm going to, again, let me show you how to do this for those of you who didn't maybe get the right answer, or for maybe those of you who got the right answer doing the wrong thing, like using illegal rules that you weren't allowed to use, some of you, I'm sure, or maybe Wolfram Alpha. But there is a particular reason why I want to do this one. And it's to illustrate a common issue, a common mistake that students often make. So first of all, let's do this properly. Okay, so this is question 1. And we're asked to find f prime of 2 when f of x is this thing, right? So x plus 4 divided by x plus 1. Okay, so we know that there is this formula for evaluating the derivative. There's actually 2 of them that we're going to have in this class. So by the limit definition, okay, we have that f prime of 2 is the limit. So I'm going to use kind of the classic one. And if you use the other one, that's totally okay. We get this thing right here, right? Now I haven't done anything, right? All I've done is write out the limit definition of the derivative and plugged in the number 2, but I haven't even used the function f at all. So now let's use that the fact that I know what f is. Let's plug that in. Yeah, exactly. Yeah, it's 2 plus h. Let me try and write it. Maybe I'll try and write it a little bit cleaner, and hopefully it won't be too much of a mess. Remember, carry your limits around. Okay, be sure to do that. So here it gets a little bit messy. So we're going to get 2 plus h plus 4, right? Everywhere I see an x, I'm going to put a 2 plus h. 2 plus h plus 1. F of 2 is pretty nice, right? So that's 2 plus 4 divided by 2 plus 1. We made the problem so that it would work out nicely. And so I'm going to do a little bit of simplification here. One of the simplifications, I'm going to do a couple of them at the same time. Feel free to scream if you're like, whoa, what the heck happened there? Okay, so I'm going to write this as 1 over h times 6 plus h divided by 3 plus h, or maybe h plus 6. You do what you want, minus 2, like that. Okay. And the one that I think usually trips up students is that we have this like fraction of fractions, and I really hate that, right? Like I don't want a fraction where the numerator is also a fraction. So dividing by h, right? That the big line, this dividing by h here, right? That's the same thing as multiplying by 1 over h. So all I've done is take this from being a fraction of fractions to just making it like a single fraction. Okay, so that's where it comes from. And then everything else is just adding 2 to 4 and 2 to 1 and that sort of stuff. Okay, so again, if you're like anything there bothers you, just let me know. I'm happy to go over it in more detail. But there were just some simplifications there. And let's do, by the way, hopefully you see if you tried to plug h equals 0 into this, you'd get 0 over 0, right? And you always will with a derivative. There's nothing you can do about that. It's pretty much designed to be a 0 over 0 thing. So we're going to have to, do some sort of factoring or something. So in this case, why don't we give it a common denominator? Okay, that's an h. So what am I going to get here? So I'm going to get 6 plus h minus 6 minus 2h, right? This is just common denominator stuff. The 6's cancel. So I'm going to get the limit as h goes to 0, 1 over h, negative h over 3 plus h. And this is great, just like anytime, if we were taking a limit as x approaches 2, we're hoping that like x minus 2's cancel. Here we're taking a limit as h approaches 0. So h is kind of the annoying thing that's getting in the way. And lo and behold, they managed to cancel each other out. So I just get the limit as h goes to 0, negative 1, 3 plus h. There, I'm now in a situation where this function is continuous. I can just plug h into it. And that gives me negative 1 over 3, okay? And that was option B. And that's how you would do that. So it's a little bit of work, right? It's a little bit of computation, a little bit of algebra, but hopefully it's not, too terrible. Now, the mistake that I often see students make here is from watching the videos that you can define f prime of c, right, for any value c. So I'm going to say alternatively, and I'm going to do this in a slightly different way, but I say alternatively, I mean, this is actually a worse way to do it. Okay, so I got a question. How did I get -6 minus 2h? Right, so that is multiplying, right, when I want to give it a common denominator, I multiplied that by that. So that was a direct message for those of you wondering, right? But to give it a common denominator, I write the right-hand side as 2 times 3 plus h divided by 3 plus h. And then if you expand the 2 in, that's how I get the -6 minus 2h. Why was h involved again? It depends on what you mean by that. Can you elaborate? So the definition of the limit has, is in terms of h going to 0. That's just the variable we use. You could call it something else if you really want to, but yeah. So the limit is always as h goes to 0. Again, there's a second definition of the limit that has like a limit as y approaches x or something along those lines. And again, you don't have to use h here if you don't want to. You could use something else, right? You could use r or s or any other letter, but h is a pretty typical one that we use. Now, some people, how did the h get eliminated in the second last? Oh, because there's an h, right? So there's an h up here in the numerator, and there's an h in the denominator, right? So it's an h over h. Like if you want, you could kind of combine these. So let's say I multiplied the h in, I would get -h divided by h times 3 plus h, right? And then the h's cancel like that. The step after that, the 3. Oh, so at this point, you can just plug h equals 0 into here, right? Like you've done enough cancellation that you actually can evaluate the limit now. Okay, cool. All right, so some of you know from having watched the videos and everything that you can define, and often this is actually a more kind of efficient, usually this is a more efficient way of computing derivatives, is instead of computing it at a specific number, compute it at the variable c sort of thing. And this allows you to compute a function which returns to you to the value of the derivative. And so historically, what we would do is we'd give a problem like this on a test, and we just exactly this problem, right? Find f prime of 2, obviously more kind of in the in-person days. And what you would see is you'd see students first compute this, right? F prime of c, and then let c be equal to 2. And there's nothing wrong with that. That absolutely gives you a correct answer. But what I want to show you is I'm going to run through this computation here in a second. And what I want you to see is how much worse this computation is. So it's the sort of thing that, like, if you're asked to do it at a single point, you should probably just do it for that single point. If you're asked to do it in general, fine. In that case, do it in general, right? But I think you're going to see very quickly here that this is much worse if you try and do it in general. Okay, it's not impossible, but it just kind of sucks. Okay, what was the function again? X plus 4 over x plus 1. So this is going to be c plus h plus 4, c plus h plus 1 minus c plus 4 divided by c plus 1 divided by h. Okay, and I'm going to do the same thing by pulling that 1 over h in front here. But hopefully, you see, this is already worse, right? Look at where we were correspondingly when we did it for a single point. This box here and this box here represent the same step. And in the top box, notice that we just got this 2 here, right? Because we just plugged in a number, and so everything canceled out, or like everything evaluated really, really nicely. Well, it's not even that it's harder to find the denominator. It's just like, here, well, look at what happens. So I'm going to do the same step here, right? Where I try and give it a common denominator, or maybe that's what you're saying. But like, yeah, when I try and do the step now of doing the common denominator, look at how terrible this is going to be. So I'm going to do the limit as h approaches 0. And you can imagine students going to make, if you're doing this by hand, you're going to make a computational mistake here, right? So this is going to be minus c plus 4. Hopefully I don't make a computational mistake. Okay, because I did not practice this before I came. Because I want you to see somebody do it live, right? I want you to know that, like, it's not all just a show. Okay, but now I have to expand out that numerator, right? Okay, so let's do that. So let's expand out that numerator. And that's kind of gross, right? I don't want to expand that out. But we gotta, what are you going to do? So we're going to get c plus h plus 4 up here. And then we're going to subtract, so c squared plus ch plus 1 plus 4c plus 4h plus 4 divided by c plus h plus 1 divided by c plus 1. Okay, so we get some cancellation here. What are we going to get? So the 4s are going to cancel. Is that it? Oh, shoot. Never mind. This is not how common denominators work. Right? I have to multiply this side by c plus 1. Oh, man. I clearly don't do enough computation in my life that I am making stupid computational errors. Okay, see, so already I would be in trouble on a test because I made a stupid screw up. C plus h plus 1 divided by c plus 1. But that's okay, right? Exactly. Ariana, sorry, I didn't see your message. If I just looked up, you would have saved me probably some trouble, right? But absolutely. All right, so now I got to expand. So it's worse now, right? Which is good. I get to make my point that how much worse this now is. All right, c squared plus c. So c squared plus c plus ch plus h plus 4c plus 4 minus, okay, so c squared plus ch plus c plus 4c plus 4h plus 4. Okay, and again, you imagine, hopefully I haven't, but you can imagine it's really easy to make a computational mistake here, right? Oh yeah, this isn't great. Okay, now what cancels here? So we've got a c squared on both sides. It looks like we've got a ch on both sides. We've got the c on both sides. We've got 4c on both sides. We've got a 4 on both sides. Okay, so there's a lot of cancellation here, right? And so this is going to be equal to the limit. Somebody tell me if I made a mistake here. Okay, so what's just left over? I got h minus 4h. So I think that's negative 3h divided by h times c plus h plus 1 times c plus 1. Again, these h's are going to cancel. So that would give me the limit as h approaches 0 of negative 3 over c plus 1 squared. Right? And yeah, okay, now, so therefore f prime of 2 occurs when I plug, c is equal to 2 in this. Oh, and sorry, there's no limit here. Right? And so if I plug c equals 2 into this, what do I get? I get negative 3 divided by 2 plus 1 squared. And yeah, that is in fact negative 3 over 9, and that is negative 1/3. Right? So this is what I'm saying. Like, I hope you appreciate that first computation, right? Here, maybe let me separate them so you can see where the line. First computation is way easier than the second one, right? Now, of course, the second one gives you a lot of power because it gives you the ability, like if I had said compute f prime of 2 and compute f prime of negative 7, then you only have to do the computation once. You only have to do the bottom computation, and then you just plug in c equals 2 and c equals 7. But if all you're asked for is c equals 2, don't make your life harder, right? Don't do the extra work that you don't have to. We all want to be as lazy as we possibly can be, right? So just do the top thing. And like I'm telling you, far and away, we'd ask this sort of question on an in-person test, a student would do it, and overwhelmingly students would screw up this step right here, right? You just make some silly little mistake. Maybe you add a plus instead of a minus or something, or miss a term, and it completely screws up your answer, right? It's also harder to mark, which just pisses off your TAs, right? So try to take the easier answer. Does that make sense? When it ever asked to do the bottom part, oh, for sure we could do that. Yeah, for sure you could be asked to do that. That's totally fair game. I'm just saying don't do the bottom part if you don't have to. If I ask you to do the bottom part, and I totally could, then do the bottom part, but don't do it if you don't have to. That's just the moral of that story, right? That's all that I really want to emphasize about that. Okay. All right, here, let's do this one. Now, there's not a lot of computation. What's the point? Oh, sure. So the point, this is a great question. So the point of this formula now, so let's say I also asked you to find f prime of -7, okay? So in the top thing, if you had done it this way in the top portion, you'd have to redo this entire computation now, but with -7 instead. The benefit of using the bottom thing is that my expression here, right? So I found f prime of c is -3 over c plus 1 squared. So the benefit of having done this is that now that I want to find f prime of -7, all I got to do is plug that into this formula. Right, so that's -3 over 36 or -1/12, assuming I did that correctly. Right, and that just saves you a ton of time, right? Like that's so much easier to do. And this is especially useful if you're asked to do a whole bunch of these f primes. It's very similar to, you remember how when we asked you to compute like the inverse of a matrix, and you might say, well, like, why would I inverse when I could just row reduce? Well, row reducing is fine if I give you one vector of constants, but if I give you a bunch of them, you kind of want to find something that allows you to do to save a bunch of time in that. And the inverse matrix was exactly the thing that did that, right? So by doing it in general, it gives you more flexibility, but often it comes with a price that it's a little bit more work. There are some things though, most functions aren't actually that much more work. It's just these rational functions that are really, really nasty and tend to do this sort of thing. Okay, so let's try this one. This is a really nice one. So the benefit of doing it this long way is it gives you a generalized formula that you can use on any number. Exactly. Yeah, that's a great way of saying it and internalizing it. Exactly. Yeah. Yeah, you can find f prime c for any c, right? So it's really, really nice. But again, sometimes it comes at a cost, right? It comes at a little bit of extra work. And later on in the course, what we're going to need to do is we're going to have to find the derivative of the derivative. And so in order to do that, you need to know what f prime is at any point, right? Because you want to think of it as a function instead of just as a number at a single point. So if you want to take multiple derivatives, we really need that general expression for what the formula of a derivative is. Right, exactly. Yeah. And in theory, you could be asked to find any number of derivatives, right? In fact, being able to find arbitrary, like if you're given a function which is infinitely differentiable, that is a thing. And there are ways, like, so for example, I think we all love polynomials, right? Like polynomials are super nice. They're super easy to work with. We love differentiating polynomials because they're really easy to differentiate, right? And it turns out, we won't do it in this class, but if you went and you took like 136 or something, they learn about something called Taylor series. Some of you might have heard about this. And Taylor series are generally the ability to write any function you want, as long as it's infinitely differentiable, in terms of a really long polynomial. And the math here is actually fairly complicated. You have to worry about things called uniform convergence and radiuses of convergence and blah, 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 blah. They're not that bad, actually. Okay, I can write out the formula for you right here. But the great thing that they win you is this ability to write functions as infinite polynomials, right? Here's the expression. I'll just write the expression down for you. So this is not related to this question. So if you're working on this question, please just continue to do it. Where's my annotate button? There it is. Okay, so the formula is that f of x is the sum. Okay, now some people are already out. They're like, this sounded cool, but you wrote down the sigma notation. I'm not in anymore. But you know, it's an infinite summation. We definitely have to use sigma notation. So you have to choose a point at which to do it. So I'm going to choose 0. Okay, and that's the formula. Right? So all you do is you keep computing the derivatives of this thing. So in particular, you know, our nice function e to the x, looks like 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial, right? It has this like very nice, very obvious pattern. Right? And so again, the math involved in like, doing the nitty gritties of this can be a little bit complicated, but like computing the series themselves usually isn't too bad, right? Especially if your function is relatively nice. So here we've written this e to the x. This is something called the Taylor series. We're not doing it, Connie. It's just kind of like for interest for anybody who wants to know like what's going on. And this idea of maybe having to compute arbitrary derivatives. This is the sort of thing where that's involved in. Don't worry about it. It's not related. But yeah, if you want to, if anyone wants to do some reading, this stuff is called Taylor series. And there is a section of the book. So if you want it from like, we did used to do this stuff in 133, but I've since cut it. So there is a section of the book, and that section is called Polynomial Approximation. And I think it's at the end of the derivatives chapter. And so if you want to kind of see some of this stuff in use, you can go and you can read that chapter, and it'll give you a little bit of an introduction to this. Okay, I'm going to wrap it up in about 40 seconds here. All right, I'm going to clear my screen. And I'm also going to just copy the functions down so I don't have to take them with me. We're only on 2. Yeah, this is only our second question. The whole thing's recorded though, so you'll be able to see what it was. Yeah, I'm going slow today because I did a fairly long computation in the previous question, but okay, let me call it there. All right, so we're a little bit split on this one. We seem to be leaning towards A. A is the correct answer, so good job, class. That being said, it'd be nice if I kind of got everyone else on board. So let's go through it. Now, this is the sort of question that you probably don't want to just do every single possibility. You can, but that's probably not what you want to do. But how are we going to do this? Here, let me just set us up here. So let's zoom in. Okay, so we were asked, right? This is the limit that we were given. So we were given the limit as t approaches 0 of the square root of t squared minus t divided by t like that, right? Okay, so if we wanted to, what we could do is we could legitimately just go through every example of this and write down the corresponding limits, right? So in the case of A, we have f prime of 0. And again, I would not suggest doing this, but I think there's a nice kind of limit learning thing here. So it's the limit as h approaches 0, f of 0 plus h minus f of 0, all divided by h. Okay, and we're told what the function is, right? The function is x squared minus x. So if we did that, we would get the limit as h approaches 0. And again, 0 plus h is just h, right? So h squared minus h. F of 0 is just 0. And then we divide by h. And there we go, right? We're done. That's it. Right? The top thing is a limit in t, but t is just a dummy variable. These are the same limit, right? They evaluate to the same number. So if you were doing it like this way, you would get lucky and you would find it in A. But let's maybe just do it for the rest very quickly. So g prime of s, like if you really didn't know what you were doing, and you could just do them all, right? So this would be g of s plus h minus g of s divided by h. Limit as h goes to 0, square root s plus h squared. Minus the square root of s squared divided by h. And that doesn't look like the same thing, right? Those don't look equal, so it's probably not B. All right, C, h prime of 1. So the limit h goes to 0, 1 plus h is 0 divided by h. So this would be 1 plus h squared minus 1 plus h. So that's the f of 1 plus h part. And then I need to subtract h of 1. Oh, that is 0, which is nice. Divided by h. And it's kind of close, but it's not the same thing, right? So it's probably not C either. And then finally, if we did D, u prime of -1 equals the limit. H goes to 0, u of -1 plus h minus u of -1 divided by h. Limit as h goes to 0, h minus 1 squared minus 1 divided by h. Again, maybe it looks kind of similar, but I mean, it's not, right? Like those are different. So the only thing it could be here is it had to be A. Why is it? Oh, you're right. It should be h of 1. Yeah, thank you. Okay, so for you to do that, you'd get this idea. Okay, there's only one answer that it could be, but this is pretty long, right? And in particular, like if I actually ask you to evaluate this limit, there is a trick. Writing it as a derivative is a nice way of doing it. So alternatively, so let's kind of come back up to here. What I'm going to say is I want this to look like a derivative. So why don't I start? Maybe let me use a different name for a function. What's a good letter? What's the letter you want me to use for our function name? Try not to use F, G, H, or U that we've already used. No, T is a bad one because it's our variable, right? I totally use T. Okay, Q, right? Okay, let's try and use Q. So this is going to be Q of T plus C minus Q of C divided by T, right? And that would make this Q prime of C. Ampersand, was that the suggestion? Like, yeah, I mean, we could have, but no. 5 I also like, but yeah, we're not going to do that either. Yeah, you people are sick. That. Why don't we use dragon? Okay, the function will be dragon of T. So yeah, so what I'm doing is when I look at this, what I'm trying to say is, all right, if I had to guess what sort of function would this be, what would it be? So immediately when I look at this, I just go, yeah, I love that. I just go, okay, look, this has to be, look, there's no like other number in here, right? Do you agree? Like I'm trying to figure out what C would be. I'm not seeing any other number other than the T. So that kind of suggests to me, that suggests C is equal to 0, right? You kind of see how I'm guessing that, right? Like I just don't see a 1 or a number 7 or something like that. That's not a guarantee that there isn't a number in there somewhere and that it just canceled out. But I'm kind of thinking, okay, C is equal to 0. The other thing I'm thinking is this. Where's Q of 0 here, right? Like this whole thing in the numerator is under a square root. So where's this thing? Oh, well, that probably suggests to me that Q of 0 is also equal to 0, right? Does it have to do with abstract math? No, I wouldn't say so. This is just me kind of like running you through how I would problem solve the question without having multiple choice, right? I'm just kind of saying like, okay, what am I doing here? So it seems to me then, so knowing this fact and knowing that C is equal to 0, that tells me that Q, I would get the limit here as T goes to 0 of Q of T minus Q of 0 divided by T. But I said Q of 0 is 0. It looks like this, right? And now if I compare these two things, well, Q of T can only be, the Q of T has to be that numerator, right? And that's how I would arrive at this answer. Right? Sure, we called it Q instead of F, but that's how I would get here if I didn't, have a bunch of options and just kind of brute force them through. I would try and reason through, how the derivative should look like and see what sort of assumptions I can make about that. Maybe my assumptions are wrong, but you make an assumption, you see if you can get an answer. And if you get an answer, great. And if your assumption's wrong, you go back and you revisit your assumptions. Okay, does that make sense? The T plus C. Sure. So that's just me saying, so F prime of C is the limit as H goes to 0, F of C plus H minus F of C, right? And now instead of writing, H, my limit in terms of H, why don't we change that to a T everywhere, right? T, T, T like that, right? Does that make sense now? So where the C plus T is, the T is just a placeholder for the H. Yeah. So does that answer it? Did I? Okay, cool. Was it U of T? Yeah, okay, sure. Yeah, U of T, nice. True. Okay, Amit, so specifically what's bugging you? Can you narrow it down? Okay. Yeah, I guess. Okay, no, like, I just want to make sure though, you do get it. You're not just saying that, because sometimes you interact with a student and they just say that they get it. I want to make sure you do get it. Let me know if something here doesn't make sense, because I'm happy to go over it again. This part of the top of the screen is a little bit tough. It takes a little bit of practice to do. This is definitely a good thing though. Have a friend make up a function, write down the definition of the derivative, and then hide the function and see if you can go back to it and cover it like that. That one definitely takes a little bit of practicing. But on the other hand, again, you could brute force this, right? Sure. So, I mean, it's basically just a guessing game, right? Like so I got a direct message being like, hey, can you basically go over this again? What I'm basically saying is I know that this has to look like right? There is no Q of 0 here. Oh, it's in the Q of T, right? So basically my argument here is C must be equal to 0 and Q of 0 must be equal to 0, right? So this is 0 and C is equal to 0. Right? Because there's just nothing else here. Like if there was T squared plus T minus 7, okay, maybe there's something here. Maybe there's something in the Q of 0, but there's just no other term, right? Like that square root, everything under that square root has to be a single term in the numerator. So that has to be Q of T, and there's no C's in there. So that tells me this has to disappear. And C is also equal to 0. Okay, so what's Q of T? Well, Q of T's got to be that thing. Okay, cool. Ahmed, are you good? Do you see? And so Q of T is this function. Right, that's where the square root went. Yeah, exactly. Q of T Mississauga. So is that good? Ahmed, you're okay? No, that's okay. Like I said, this one's a little bit trickier to do. Here, let me give you a couple more, and I want you to practice them. Okay, so here, let's just do a couple of practice ones. And so this works for everyone in the class. Anyone can practice these. So let's do the limit as s goes to 0 of e to the s minus 1 over s. We could do the limit as x approaches 2 of x squared plus 2x divided by x minus 2. And let's do one more. So the limit as, let's do h approaches 0 of sure. No, that should be an h. Okay, so here are 3 practice questions. Where does the t in the denominator go? It's still there. I'm just, right, the question said figure out what the function is and where you're differentiating. So the fact that the t is in both the denominators is just tells me, okay, these are probably the same function that I'm comparing. And so, I'm just trying to figure out what this thing is, right? I'm not trying to evaluate this limit or anything. I'm just trying to figure out what should q of t be so that I can write this function as a derivative. Okay, so I claim each of these limits is the derivative, or is the limit definition for some derivative, for some function. So is the limit definition for the derivative of some function, right? Determine the function. Okay, so I want you to give these a shot, and then just because we're running out of time, right? And again, for anyone who wants to hang out in terms of, no, there's no integral yet, no. But in terms of anyone who wants to hang out in office hours, like I'm happy to pick up these as well. But if anyone has to run, write these down. And then if you're struggling with them during office hours, or sorry, during, post something on Piazza, and, we're more than happy to kind of take them up. So these are all good examples for you to try. And this is an H, just so we're clear. This is an H, and this is an H. Yeah, there's an integral thing like this, Brandon, but it's not this, yeah. Okay, so Curdy, sure, I see it. Does anyone have, yeah, for sure. 6-1F. Okay, well, everyone. So for those of you who do have to run, that does take care of the lecture for today. Okay, and of course, our next hour is office hour. So if you want to, hang around for a little bit, I'm happy to talk to you. A8, 5, 6, 8. It's hard to make these examples, Curdy, so it's going to be a little bit tough to give you anything. 6-1F. Okay. Okay. So let's see. A8, huh? Yeah, that's Dexter, who's apparently really upset that he's not allowed in the room. Right, because you can see her little head. She's not meowing. She's not freaking out at all. Okay, let me pull up the assignment here. So 5, 6, and 8, huh? Okay, so. Oh, okay, sure. Right, so 5 is like, okay, yeah, sure, we can do, I think, one like 5, where we just do a different function. So, this is kind of like A8, 5. And let me see, so we said e to the f of x. Why don't we do something a little bit different? Let's do something like the limit as x approaches 1 of ln g of x. Okay, so this is a question we absolutely could have asked you, right? It's very similar to 5, but it's different enough that I think we can talk about it. So, so this is still from assignment 8. So I want to use the g of x that is in that assignment. Can anyone tell me what should I do at this point? Like, what's the idea? What's the critical thing to do? Yeah, absolutely. Yeah, it's a composite function. And in particular, what do we know about? Yeah, exactly, Ariana. We can take the limit inside precisely because ln is, so find the limit as x approaches g of x. Yeah, we could do that as well. But so very much when we were doing the limits, like from the writing assignment and stuff, we had to figure out what the internal function was doing. But we were often limited in doing that because the outer function wasn't continuous, right? But you remember the other day, last week, when we were talking about if the outer function is continuous, I can take the limit inside. Exactly, exactly, right? Ln is continuous on its domain. So we can take the limit inside the ln, right? Since ln is continuous at 1. Well, since ln is continuous at, we'll see. Since ln is continuous, okay? And now what is the limit as x approaches 1 of g of x? Just from, inspecting the graph. Exactly. Does that make sense? I don't know quite what you mean about bringing the exponent down. It's not that you're going to, like, here, think about it like this. So e to the f of x is the same thing as, maybe let me write this differently. So let's say, let's let h, no, h is already a function here, right? Let's let, u. If u is e to the x, then u of f of x is e to the f of x, right? So this is also a composite. Right, so we're just going to do the same thing. I don't want you to think about like bringing exponentials down or anything. It's a composite function, so you basically do the exact same thing that we did above, but now we've got the exponent instead of the logarithm. Okay, cool. For 6, yeah, you do something very similar. Right, exactly, Brandon. Yeah. 6 is very similar to 5, except now you have, f of g of x, but think about what f is doing. Is f continuous? Maybe it is, maybe it isn't. F of x, no. Gerber tap, yeah. Think about, right, because you need to do a limit, right? So yeah, be careful about that, right? Because it's not, your composition is not continuous. So for f of x, as x approaches 0 to the right, f of x approaches infinity. Yep, that's right. Or just does not exist, if you prefer, right? But yeah, the numbers are certainly getting bigger. Yeah, okay, so 6 is the same sort of idea, exactly the same sort of idea as 5. It's just now instead of being given the, e to the x or ln x, you're given sort of an arbitrary function. 8 is, okay, 8 is definitely trickier. You have to, f of 1, there's no point, but do we assume it's 1? No, there's totally, f of 1 is totally exists. Yeah, you're definitely going to need the infinity thing. That's true. There's kind of like no avoiding that. Yeah. Curdy, exactly. Yeah. So it's true. Like 8 does require some knowledge of like vertical and horizontal asymptotes, even though we didn't explicitly cover them. But you can kind of get around just by hand waving it. We're totally fine with that. Just explain the general behavior, right? And we're okay with that. Like we do expect you to know that e to the x, goes to 0 as x goes to negative infinity, for example, without explicitly talking about how you might compute horizontal asymptotes. You should know that about e to the x sort of thing. Okay, so 8 is a little bit more work, but it's the same sort of stuff. Yeah. Right. Is everyone okay with that? Does everyone understand what I mean? Because that is a critical point. Like you do need to know that, right? So, when we talk about horizontal asymptotes in this course, a lot of it is like, how would you compute horizontal asymptotes of complicated functions? I do expect you to know, though, that e to the x basically looks like this. And so the limit as x goes to negative infinity, right? Basically, as x becomes really, really small, of e to the x is equal to 0. And there's in some sense in which we just kind of take this as being assumed knowledge, because we're not asking you to do any tricky techniques that you might need to compute horizontal asymptotes. This is just a thing that hopefully and if you don't know, well, I'm teaching it to you right now, and you can use that. You can just assume it. You don't have to like do any math for that. You just it's true. Yeah, sure. E to the negative x is, e to the negative x looks like this, right? So you reflect in the y-axis. So e to the negative x, not upside down, because it's still positive, right? Like e to the anything is going to be positive. So it's not that it's upside down, it's that I mirrored it like this, right? Like I went like through the y-axis. If it was negative e to the x, right? So this is y equals e to the negative x. The upside down portion comes when you take negative of it, right? So if you did negative e to the x, would be like that, right? And then we might as well finish it, right? This is y equals negative e to the negative x. No, Curdy, those are different, right? Different functions. Right, so sure. So the question is, how do you do 5? So for 5, right, the critical idea here is that ln is continuous. And we said, here, maybe let me just recall. So this is from last week. If f is continuous at g of c, then the limit as x approaches c, f of g of x, is f of the limit as x approaches c, g of x, right? Gerber tap, right? That makes sense? You remember that? I think it was in Thursday's lecture that we talked about this. So if the function is an exponent, the limit can still be distributed in. Same, it kind of depends on what you mean by distributed in, but generally, yes, the exponent functions are continuous, and therefore you can take the limit inside. Well, no. So what you did, though, is you assumed that this function was continuous, and so just plugged in c, right? But that's generally, for g, this is fine. When you were doing it for f was not continuous at 0. Does that make sense? Like this isn't equal to g of c unless g is continuous. All right, so Gerber Top, give me some feedback and let me know if that makes sense. Well, so in your case, you have to figure out what the limit of f of x is, right? And so once you figure out what the limit of f of x is, you'll be good. Okay, Rafid, good to hear. Good to hear. And so, unlike, so in our question, g of x was actually really nicely behaved at, when x was equal to 1. Unlike that, in question 5, f of x is actually really badly behaved at 0, right? And so you're going to have to basically make some sort of argument. That limit, it seems like it probably doesn't exist. So you should just try and make an argument for why e to the f of x probably doesn't exist, right? Something along those lines. Hala, I'd recommend emailing Aziz for that. Sometimes the markers do stupid things. I actually check their marking, but I only check the first like 30 problems of their marking. So sometimes I miss some stuff. But email Aziz about that. Just check out there's a page that gives the instructions for how to request a remark, and Aziz's email is in that. So just take a look at that. Yeah. Curdy, sorry, I'm just getting to, because there's a bunch of, it's one of those things again where like none of the rest of you can see the direct messages, so I'm just trying to make my way through them. So if we can bring so Curdy, back to your original direct message, not your most recent one. Yes, that is exactly right about taking the limit inside. That's absolutely correct. But isn't the limit as x versus 0? No, Curdy, that's true from the left, but not from the right, right? And Hala, yes, his email is on Quarkus. Like if you go to the request a remark page, his email is in that page. From the right? No, from the right, f of x goes off to infinity. Rafid, more than 3 what? And then I got a direct message was, how do you describe an essential continuity? It depends on what you mean by describe. The formal definition for an essential discontinuity is C is an essential discontinuity of f if one of its one-sided limits does not exist. Right? Oh, I see. No. Yeah, not more than 3. Yeah. I mean, you can say, like, if I give you a graph of something, right, and it looks like, let's say it looks something like this. This happens at some point. Let's say this point is equal to -2. You would say there's an essential discontinuity at -2, right? Like that's how you would describe where it is on the graph. Yeah, exactly. Yeah, at x equals -2, there is an essential discontinuity, and you would make the argument that, in this case, neither one-sided limit exists, but, all you really have to do is that one of the one-sided limits doesn't exist. Kelly, can you narrow down specifically? Yeah, because you came in, but I don't know exactly where you came in. So can you talk about, like, tell me what specifically is where maybe you kind of got lost, or just what part of this conversation? Oh, but then since they're both right, exactly, Curdy. Yeah, exactly. It doesn't exist. Right, but not e to the negative infinity, e to the positive infinity, right? No, same. So remember, so essential discontinuities can only happen in the domain of a function, so they can only be on the x-axis. So generally, we don't talk about, we don't look at the y value when we talk about discontinuities, right? We only talk about what point in the domain of the function has a discontinuity. Yeah. Okay, so Kelly, I think you're the only one that I'm still kind of behind here on. Okay, so I saw at the beginning of the board, question 5, but how can we? Right, okay, so you have to try and figure out like what is e to the f of x doing, right? So first of all, e is continuous. So you've got some sort of idea, you can probably take the limit inside. But the bad thing here, the place where we start to run into trouble is that f of x is probably, like, it definitely doesn't look continuous to me, right? And hopefully I didn't give too much away there, that's part one. But f doesn't look to be continuous at 0. So you kind of have to figure out what is e to the f of x doing, right? Like, is it maybe try to look at one-sided limits too. Come on, dude. Anyway, so maybe look at the one-sided limits, very similar to the sort of thing that we did in the writing assignment. Look at what e to the f of x is doing as as x is approaching 0. What is f of x doing? As I approach 0 from the right, as I approach 0 from the left, what is f of x doing? All right, so very, very similar to what we were doing in the writing assignment, maybe for that question. Right, because that's a little bit different. Like the example that I did here, because this is when I say A8 question 5, I was doing a different problem, right? Because I didn't want to do the homework problem. And so I was doing a different problem where that inner limit was much better behaved. And that was the idea there. So I was using the same g of x as the assignment, but I was using ln instead of the exponential, just to try and give, something similar. Yeah, still confused on how to approach 8. Well, let's see. So h of g of x isn't too bad to look. Well, let's put it this way. Yeah, how do I want to put this? How would I want to describe h of f of x? Oh, sorry. It's just asking at x equals 0. Sorry, that's a little bit better. So how do you determine if a limit exists, first of all? Right. So first of all, you can compute what h, let's think about h of f, okay? What is h of f of 0? 5.11. Okay. Is that right? Okay. So everyone, hopefully you computed what h of f of 0 is, right? And you want to know, is this the same thing as the limit as x approaches 0 of h of f of x, right? Because this is what it means to be continuous, right? This is the definition of continuity. So if this is true, so you need to compute this limit and you need to compute this number. If these two things are equal, great, you're continuous. If they're not equal, then they're discontinuous, and you have to classify the type of discontinuity. But the definition for the type of discontinuity always involves you computing the one-sided limits, right? So what you're going to do is you're going to compute this thing, right? And you know how to do this. This is exactly the sort of thing that we did. Remember, we had a bunch of poll questions like this in week 1. Your writing assignment was like this in week 2, right? You're hopefully somewhat familiar with how to compute this thing. And then you're going to compute this thing as well. From the left. If these two things are equal, but are not equal to h of f of 0, that's a removable discontinuity, right? If both exist but are not equal, that's a jump discontinuity. If one of them does not exist, that's an essential discontinuity. So you have to compute this, you have to compute this, you have to compute that, right? And then determine, are these two things equal to h of f of 0? Or if not, what sort of discontinuity are they? So does that make sense? Does that help? And the way that you attack this is almost exactly the way we did the writing assignment and the problems that we did, at the end of week 1. Okay. Because if there's nothing here, I'm going to go to Owen's question, which was 6-1, but I have to pull it up. Ooh, oh, and this is a great question. But it says c equals -1. Okay. So yeah, everyone, if you still have, oh, you're right. This should be an x. Thank you. Yeah, thanks for that pointing out. I got confused. Yeah. Okay, Kelly, let me come back to that in a second because Owen's been very patient. But okay, actually, maybe I can answer it quickly. Okay, sure. So, I mean, think about it like this. So let me just try and answer this quickly. Owen, I'm sorry, just give me 1 second. So if you have something like f of -x squared, no, let's do something else. Let's just do -x. So what happens, you can think of this in 2 ways. First of all, if you take -x into your function, that reflects the function about the y-axis. So if you want to think about it in terms of its graph, f of -x does this. Whoop, and just flips everything about the y-axis. So if you want to think about it like that, you can. Otherwise, what you can think of is as x approaches 1 from the right, like what are we doing? Like we're taking numbers like 1.1, 1.01, 1.001. And when I plug those numbers into f of -x, what do I get? I get f of -1.1, f of -1.01, f of -1.001, right? And I can figure out what these numbers are or what this is doing by the graph. It seems to be approaching, as x is approaching 1, that seems to be the same thing as the inside approaching -1 from the left. Do you see what I'm saying here? Okay, so x is approaching 1. And if we take like a candidate set of points, that's like 1.1, 1.01, 1.001. There, I'm approaching 1 from the right. So approaching 1 from the right. Okay, let's not even worry about the f. So what happens if I take these things and plug them into the inside function, -x? Okay, so if I now look at what -x is for these numbers, they're -1.1, -1.01, -1.001, right? All I did was throw a minus sign in front of all those numbers. So there's nothing crazy going on there. What are these numbers doing, right? Like as I'm moving along the line in this direction, what are these things doing? Well, they're approaching -1, right? But they're always less than -1. Do you agree? Does that make sense? Like those numbers are getting closer and closer to -1, right? But all of them are less than -1. So I'm approaching -1 from the right or from the left. So for us, and this value of f of x, Agam, no, it would be like -0.5 or something. Right? The f of x in the problem looks like right, and here's -1, and then here's -1. And so as I'm approaching from the left, it's whatever this value is, which to me looks like -0.5. Is that okay? I know what you're doing, but can we do the limit law of that question Yeah, totally. You could do, yeah. Well, if you know both limits exist, you can apply the limit laws, Kelly, for sure. Right? Like that's why I say explicitly in the instructions, like if you use the limit laws, use them. But totally, yeah. If you remember to use the limit laws, though, you need to know that both functions exist first, right? And if you know that both functions exist, then you can use the limit laws. So you just have to verify both of them exist, and then totally you can use the limit laws. No problem. Okay, so Owen, thank you. You've been very patient. Hopefully you're still even here. I haven't really even checked. So this is 6-1 f. And this is a great problem. I really enjoy this one. So we've got the function f of x is equal to x times the absolute value of x. And the question is find, f prime of -1. Okay. So there's a cheating way to do this, and there's the long way, right? But they both basically amount to the same thing. So at -1, here, let me remind you. I'm trying to think of the best way of saying this without inducing any confusion. So the absolute value of x, let's just write this down. Always write this down, okay? If anytime you get an absolute value, until you're a master at manipulating them, just write this down, right? So this is the definition of the absolute value as a piecewise function, right? And I'm trying to compute the derivative of the function near -1, right? So which regime am I in? Am I in the top regime or am I in the bottom regime? Like which of these two parts of the piecewise function do I want to use? Bottom one, right? Everyone agree? Because -1 is less than 0, right? So we're going to use this. And when I'm taking a limit near -1, I can guarantee that I stay less than 0, right? Because we only care about what's happening near -1. We don't care about what happens far away from -1. We just care about what's happening near -1. Okay, so we're going to use the bottom. So now when I take f of x is equal to x times the absolute value of x, I'm going to replace the absolute value with -x. Does that make sense? In fact, this is true. So in fact, f of x is equal to -x squared for all x less than 0. Does everyone agree? Does that make sense? Okay. So what's the derivative of -x squared at -1? Close. Oh, but yes, Brandon, but at -1, what is it? So that's the derivative in general. Exactly, it's 2, right? So Owen, does that make sense? Are you even still here? Let me just double check. Oh, I think Owen might have lost him. So it's okay. He can check in the video, hopefully. Yeah, maybe we just took too long on the first bit. But does everyone get that? Like why that makes sense? In fact, yeah, you can actually write, so you can imagine if you did the same sort of thing, what you get is x squared if x is greater than or equal to 0, and -x squared if x is less than 0, right? And you can actually graph this thing, right? I think you all know what these functions look like, right? You kind of like draw a parabola for -x squared, and then you switch and you draw a parabola for +x squared. And here you go, right? This is what the function looks like. When you do h of g of x and plug the 0 in yet, and we don't have that value from the piecewise function. Yes, you do. You totally know what h of 1 is. No, h is a piecewise function. So which part of the function h is 1 in? All right, like which of those three functions for age correspond to when x is equal to 1? No, the second one is x equals 0, right? It says h of x equals 1 if x equals 0. Look at the if part. So what, -2 over x, right? Right, exactly. So when you're trying to evaluate something, here, let me choose a different number. So if you're trying to figure out what to do for this, you say, oh, that number, that's bigger than 0. So I'm going to use this function, right? If you're trying to do like -3, you'd say, oh, well, that's less than 0. So I'm going to use that function, right? So yeah, you do know what the value of the function is. Okay, perfect. Okay, somebody asked for 511. I'm sorry, I don't remember who. Now, when you said 511, what did you mean? Like example 511 or like 5-11 from the exercises? Like what is 511? Whoever asked it. Because example 511 is vertical asymptote. So we don't maybe want to do that. And 5-11 is also, yeah, horizontal and vertical asymptotes. So that actually shouldn't be in the reading, everyone. That is my mistake. When I was doing the readings for this week, I think I accidentally put question 11 in, and it should not be in there because we did not do that. Actually, so I'm just going to take it out of the readings right now. Let me just do that. Wait, what? Wait, yes. Lest I confuse more people. Okay. For question 6-2, how can we find the function f is differentiable? Did I close it? 6-2. Right. So this is a good question. So for example, if you look at 6-2, the question is for each function in exercise 6-1, determine where the function is differentiable and find the general form of f prime of x. So the trick to this is just find f prime of x, and wherever that function is not defined, your function is not differentiable. So for example, if you compute your derivative in general and you get this, right? The only place where this is not defined is when x is equal to -1. So that would be where your function is not differentiable, right? That's how you would do that question. Does that make sense? Person who direct messaged me? Just find f prime. Yeah, Hala, exactly. Don't worry about it. This is just like a direct message. So not differentiable means it can't be differentiated, right? So you're differentiable if this number exists. You're not differentiable if this number does not exist. So if I'm asking you, where is this function not differentiable? I'm asking you, find all the places where this number is not defined, i.e. where this limit, find the values of c where this limit does not exist, right? But this is a lot of work. So it's way easier to just compute this thing and determine where that function is undefined. And in our case, that function is not defined at -1, right? Because it's not defined at -1, that's where it fails to be differentiable. This function is defined for every other value of x. Okay, so same, it was just kind of a general question about 6-2, which is how do you determine where a function is differentiable? And that's the answer for it. Okay, so Kelly, are you okay? Does that make sense? Okay, cool. Ariana, I probably missed this question on crowd work. There are two. Right. So I actually fixed this, Ariana. So if you go and check it now, it should be more clear. And I did email everyone who had already submitted to make sure that they fixed it as well, but it was only like 6 students. So if you go back into CrowdMark now, it'll say which, and it is exactly what you wrote down. It's 1 to 4 for question 1 and 5 to 8 for question 2. Yeah, at least it should show up that way. Like if you go and check, and if it's not that, let me know. If we're not in office hours, send me an email and I'll go fix it again. Question 8 is related to the graphs though, right? Yeah. Assuming you're talking about the assignment. Yeah, it still is. Okay, anyone else? Sure. Yeah. The assignment questions are labeled. Okay, I guess. I don't know what you mean by that, Don. Oh, sure. Right. Yeah, exactly. Like on CrowdMark, you mean? Or yeah, exactly. Oh, I see. You're confirming for me that CrowdMark does look correct. Right. Yeah, perfect. Thank you. Okay, does anyone have any 133 stuff? Because there's at least one 102 question. At f of 0, let me just double, I need the graphs. What are you doing, mouse? Stop that. Assignment 8. No, Kurdi, it's not. Double check what the definitions for those things are. Yeah, like you've computed your one-sided limits correctly, but you've misclassified it. Okay. I mean, Kelly, do you have a specific thing about that you want to ask? Because it's basically, right, like you're continuous at f is continuous at c if this is true. Right? If this is not true, then your function is discontinuous, right? Or not continuous. So the definition of not being continuous is that this is not true. And then the classification of discontinuities is an additional thing, but try and tell me exactly where the issue is happening. I had a question about 4 from the assignment. Okay, sure. So what about 4? No, it's not, Curdy. I mean, by process of elimination, it could only be the other thing, right? So what's the definition of removable? Yeah. So the limit exists. That means both one-sided limits also have to exist, right? And they have to be equal. No, Sam, not you, not yet. Sorry. So Curdy, right? For the limit to exist, the two one-sided limits both have to exist and they have to be equal. And that's not true in that case, right? Right? But infinity is not exists. Infinity does not exist. It's just a special kind of does not exist. Yeah. To exist, you have to be, no, like it's fine. It's kind of ambiguous and totally don't worry. That is a mistake that students have been making for literally as long as I've been teaching and almost certainly for decades before that. And the problem is the use of the equal sign, right? So if I write this and people see equal, they assume that means it exists. This does not exist, but does not exist in a very special way. Do you know what I mean? Exactly. Yeah. Infinity fails to exist. If it's equal to infinity, we're saying it doesn't exist, but it doesn't exist in this special way versus there's other ways that a limit could fail to exist, right? So this is us classifying further how the limit might fail to exist, right? So yeah, this does not exist. No problem. Same. If we were to, no, you have to look at what happens near, not at, and that's obviously very important for the function f, right? Like that's not a big deal for g, same, right? But it is a big deal for f. So you have to look at what's happening near, not at. I mean, it depends on what you mean by doesn't exist. But like, so okay, so it's true, f is discontinuous there, but the limit does exist, right? And like you say, like if you look at what happens from both sides, the two limits both exist and are equal, right? The one-sided limits, that means that the two-sided limit also exists. Yeah. And you'll notice, for example, the limit laws don't say anything about continuity. It just says the limit has to exist. Mm-hmm. Kelly, yes, exactly. That is exactly right. Yep, same. Yep. The limit laws say nothing about continuity. Yeah. It just cares about the limits existing. Yeah, Kelly, that's exactly right. Do G at 0 for me as well, just so I can make sure that you get it. So yeah, tell me what the discontinuity of G at 0 is, just so I'm certain. So it kind of, you have to make that call. Same, it's kind of hard when you're doing discontinuities. For sure, do them from both sides, right? Other than that, it depends. You should avoid doing both sides separately if possible, but sometimes you can't avoid it. Like, don't do twice as much work if you don't have to, right? Do the limit in a single thing if possible. But sometimes you don't have a choice, and you kind of have to break it down into its one-sided limits. When that happens, you got to do it. Discontinuities for sure is a rule. If you're trying to classify the discontinuity, look at the one-sided limits always, right? Like you can use that as a hard and fast rule. Yeah, sure. Yeah, it'll give the same answer. So if you really want to like do the extra work just to be doubly, triply sure, you can do the separate sides, but it is just more work, right? And is often unnecessary. I think like if you do a couple, as you do more examples, you'll hopefully start to realize when one-sided is appropriate, when it's not. But if in doubt, yeah, you can always just do one-sided and you'll get the right answer. No problem. No problem. Okay, anyone else? No problem. See you, Tudor. Kelly, exactly. Good job. All right, Sam, see you later. So Kelly, yeah, I think you got it. So yeah, that's a good one. Yeah, no problem. For Simon, part 6. Yes, yeah, that does make sense, Christian. And in particular, though, be sure when you justify that, why can you just plug that number into F? Right? Like what property of F allows you to do that? See, Ariana. Module 6. Like chapter 6, like derivatives and all that. Oh, I'd say it's pretty short. Yeah, it's probably like 3 weeks. It's not long, but some of the stuff in there can be hard. There's some easy stuff in there and some tricky stuff in there, but I've got some tips about how to deal with the tricky stuff, so it's not too bad. Mm-hmm. Christian, exactly. And make sure that you say that, right? So Christian, that is exactly what you want to say when you write that down. Okay, so make sure that you include that, because that's the justification behind why you're allowed to do that. No problem. Okay, sure. Yeah, numeracy question 4. So that was the one with the weird, like, sawtooth thing, right? And it looked like this. Right, and so this was like -1, -2, -3, something like that, and 0, 1, 2. So, I mean, there are a couple ways that you could do this. For me, what I did is I basically looked at the function here, and I said, oh yeah, that's the absolute value of x. Right? And then I said, okay, well, let's now look at the interval 1 to 3. So on 1 to 3, absolute value of x. So it's the same thing on the interval 1 to 3, but I had to like shift the absolute value down, right? So it's equal to the absolute value of x minus 2 on 1, 3, right? And then if I did this for the next interval as well, it'd be f of x is equal to the absolute value of x minus 4 on 3, 5, right? Does that make sense? And of course, you could do the other direction as well. I'm just kind of focusing on the right here, because what I basically want to be able to say is, look, on this interval, I'm going to use this, the absolute value of x minus something. And what is that something? Oh, it's the midpoint of that interval, right? And so what I could just say in general is then f of x is equal to the absolute value of x minus something. I don't know what the something is. On, okay, now I need to figure out a way of doing this. It looks like these are always odd numbers. And the way that we write odd numbers is -2n plus 1, or sorry, I think 2n minus 1, 2n plus 1 is the best way to do that, right? So for different values of n, right, you get different intervals. So for example, -1, 1 happens when n is equal to 0, right? 1 to 3 happens when n is equal to 1, and 3, 5 is n is equal to 2. And the number that I use here is always the midpoint of this interval. Well, the midpoint of that interval is that. And that's the answer. Mm-hmm. Cool. Yeah, so Dad, like I said, term test 3 or term test 6, we'll worry about it when we get to it. It's, like I said, the stuff there is a little bit tricky, but it's not too bad. I think you'll be okay. It's fairly algorithmic in the sense that we can't ask you too much theory because the math behind that section is too hard. So we can't ask too much theory, if I remember at least correctly what stuff is on that. So yeah, I wouldn't worry too much about it. We'll worry about that when we get there, right? All right, Brandon, I think we're, yeah, no problem, Kelly. See you later. Right, yeah, for sure. Yeah, it's definitely a little bit tight. Brandon, I think the 133 stuff is done. So if you want to ask your 102 question.
Are you okay with me unmuting because it's
Sure.
easier if I just say it? All right.
Yeah.
So I'm working on this set thing, and I think I understand what it is, but I'm just not sure I got the logic right in my head. So I want a clarification. I know you said you can help me with that. So
Sure.
I was wondering. So the set is this first part's in brackets, A, XA, so the Cartesian product,
Okay. So A cross A.
Yeah. Oh, you say it as cross? Okay, that's good to know.
Sure. Yeah.
And then that's in round brackets. And then you take the difference, so that backslash of B cross B.
Okay.
And that's also in brackets, yeah.
Sure.
And then A and B could just be any set. So for example, like in my mind, I had A as the real numbers and then B as the integers.
Sure.
So A cross A could be just any pair of real numbers, and then B cross B could be any pair of integers. So when you take A cross A and you take the difference with BXB, that is just all pairs of real numbers that aren't like pairs of integers.
You have to be a little bit more precise, but yes, that would be right. It's that neither can be an integer.
Right. The thing I was wondering though was, could this like also, is it fine if one of them was an integer, say like 2, but the other one wasn't?
Right, exactly. And so that's the point I'm trying to make. No. Wait, let me double check that. Yeah, no, the answer should be no. Yeah, neither of them can be. So what you've done, right? So you've taken R cross R and you've removed Z cross Z, right? So you said, I've taken out absolutely, well, okay, let me double check this. Yes, actually, yeah, sorry, one of them could be. Because Z cross Z is just the integer lattice. And so why? Yeah, they absolutely could be. Yeah. So all you've done is take out things that look like this, right? Where M and N are both in Z, right? But notably, you haven't taken out. So what you want to do is, if you want to check that like 1, 2.5 is in this set, right? So this set is everything in R cross R, but you've removed everything in Z cross Z. So the only way you're not in R cross R is if you're in here. Right? Because those are the things you took out.
But one of them isn't an integer, so it can't be in Z cross Z. So it has to be in the whole thing.
Yeah.
Right. Okay, because I wanted to make sure the logic there was right, because I knew if I wrote that down, I might have got it wrong if I didn't double check my logic.
Right. Yeah. And there's like visually, this picture is not too bad. So you've got, here's your first copy of the real line. Here's your second copy of the real line, right? So R2 is R cross R. And you've now removed the integers. And you've removed it from both sets, right? So what you've removed are these things.
Right.
Okay, so visually, this is what's happening. And now your question is, right, like, so here's 1, 2.5 right here. Right? And you can see it's not one of the blue dots.
Yeah.
Right? So yeah, that's totally okay.
So it's in it. All right.
Yeah.
Okay, that's good. All right, that's perfect. Thank you so much. I appreciate that.
Yeah. Okay, anything else? Otherwise, we can call off SARS a little bit early. No problem, Curtis. See you later. All right, Brandon, see you. Dad. All right, everyone. I guess we're going to call off SARS. So thank you for coming, everyone. Have a good Wednesday, and I'll see you Thursday evening. Okay.